is intended to give you an idea of what we covered in class and also the questions that came up from students as we looked at the homework from last night. So we're looking at page 296, 38 through 42, and that's what you see right here. So let's go to it. This is the first homework problem, and it's very representative, and I think you'll find that this is pretty easy to understand and will help you get over what you did with double replacement. Actually not getting over, but seeing how things are different with other reaction types. The reaction types that you dealt with last night, you were dealing with acid-base, and you were told that it was acid-base. So this pointer will be useful, and that is that right here we see a hydroxide ion making this a base because the hydroxide is on the end of the molecule. Here we see a sulfate ion at the end of the molecule. On the other end we see the hydrogen ion, and hydrogen then is going to wind up being are making this molecule an acid. Sulfuric acid is its name, as on your memorized ion sheet, and hydroxide here on your memorized ion sheets. Now, whenever you have reactions that form water, those guys are almost without exception going to be acid-base reactions. So here we have the base part of water. Always write your water this way, the way you see in black above the blue H2O, because when you go to balance your equation, you can see that this guy is your hydrogen, and don't think of this as hydrogen at all. This is hydrogen together with oxygen in what we call the hydroxide ion. So that will make all of your balancing much easier. As you can see, when you do this 2 H's on the left side because of the subscript 2, and then you go over to the right side and you see this with a coefficient of 2, you know that your hydrogens are balanced. And then you say, hey, wait a minute, Mr. Wigger, this guy has hydrogen too. No, it doesn't. Now, does that surprise you? Good. Because I want you to unfasten your thinking from water having to be like this. When water is like this and H is in a hydroxide ion, balance the whole ion, not the hydrogen, because hydrogen is just part of the hydroxide. So this 2, because of the 2 coefficient here, 2 hydroxides balances with 2 times 1, 2 hydroxides, and everything is good. Now this guy is going to be aqueous because this is potassium sulfate. And potassium sulfate you're not going to see unless you evaporate all the water. So this guy is your acid-base reaction, and what the book refers to as reactions that form water. But the other thing that's always formed with an acid-base reaction is a solid, not a solid, I'm sorry, a molecule that we call a salt. This is a salt because it's a metal with a non-metal ion. And this ion has no metals in it, sulfate. This ion is the metal potassium. So there we go. We're in good shape, I hope, on this part. Now let's go to the complete ionic equation. This is just taking these guys apart. Here's the first one. Here he is taken apart. Here's the sulfate taken apart. Here's the potassium taken apart. Here's the hydroxide taken apart. Here is the water. Now you'll notice that that is not written even in the complete ionic equation as ions, because this is what made the reaction go. And because it made the reaction go, it's not going to separate. But the potassium and the sulfate, which form the salt, potassium sulfate, these guys have to be separated. And we show their charges in the top right corner above the ions. See, every one of these is in the top right corner. The reason I put charges above, I didn't have them above and to the right, was just so that you would know that what those charges are. Normally, when we write equations like this, we don't put charges. But it's very helpful if you don't know what the right side is, the right side of the equation, the products. If you're not told both of the products, which you weren't in these questions, then it's going to show up this way. And it will show up because the sulfate and the potassium are not part of the water. And so they become the salt, which most salts dissolve in water very nicely. Okay, so there's our complete ionic equation here. Now let's go down and let's look at the net ionic equation. And here in the net ionic equation, you'll see that I have hydrogen, hydroxide, and water. And you say, wait, Mr. Wigger, why is that coefficient 1? Because up here, where you see hydroxides, he has a coefficient of 2. Well, if I multiplied everything here by 2, wouldn't I get 2, 2, and 2? This is a 1. It's a little crunched up, but let's go ahead and fix that. Okay, now that 1 looks right. So that's the coefficient of 1, 1, 1, and we could have a 2, 2, 2, but we have to reduce any ratio to its smallest possible ratio. So if we had 2 to 2 to 2, it has to be 1 to 1 to 1 because all of them would be divided by 2. And that's how we do the net ionic equations. Now, to get rid of the spectators, these guys are spectators. I've circled them up here. The water here is told as the driving force, or it's told that that is the main product, most important product. So if this is our product, the way we get these guys is simply to rewrite this as HOH. So here's the hydrogen ion and here's the hydroxide ion. And since we have one of these that is water, a water molecule, this HOH comes back over here as the hydrogen ion and the hydroxide ion. And so they wind up with coefficients of 1. Notice the AQs. Okay, those AQs tell you that these guys are aqueous. They're dissolved in water. But as soon as the reaction is going to the right, like this, and the water is on the right side, we are absolutely good to go. So that's the acid-base reaction. Now, the next thing that you want to get down, because we showed this in class, is this entire slide. So at the beginning, let me just show you. Okay, we have last night here. Last night was reactions that form water, and these guys are acid-base. Before is like last week when we were doing precipitates. The precipitates, we abbreviate as PPT. That was the before stuff. This is what we had with double replacement reactions. And double replacement reactions, if they go, are definitely going to be forming precipitates. So let's also write this as DR for double replacement. So now we go back down here, and what did we do last night? These were reactions that form water, and those are acid-base. So it's always water and a salt. And so let's write that in. And a salt, which in the last reaction that we just looked at was potassium sulfate. I believe, let's go back and look. Yeah, potassium sulfate, which you see right here. That's our salt. And although this is aqueous, we could make it into a solid if we evaporate all the water, because then it can't be aqueous. And that will form a powder, and that we can call our salt. And so that's the salt. Acid base always forms water and a salt. Now tonight we're doing reactions that form gases. Those are almost always ox red because there will be an element on one or both sides. Element on one or both sides. Now let's look at the big picture here. We see that why reactions happen is because certain things are formed. Precipitates, which happen with double replacements, that we call precipitation reactions. Water, which is the reactions that form water, which are acid-base reactions. Gases, which we're going to be looking at tonight. And gases could be all kinds of stuff. It could be carbon dioxide, that's a common gas that's formed, CO2, or it could be oxygen, or it could be hydrogen, or any old gas you like. If it forms a gas, that means that it's probably going to be oxidation reduction because so many of the gases are elements, but not always. But that's something to look for in certain reactions. So these are all known, these things up here are known as driving forces, the formation of any of these, okay? And that's pretty much what we did today. We also had Mrs. Josh on in to talk to us about AP Chem. And one of the most compelling reasons I know of to take AP Chem is the difference. So we're off chemistry now. If you're not interested in AP Chem, you can stop the recording. But you might want to take a little look here because what I'm going to do is show you some stuff that might be helpful for your future. And let's get that little guy as a thicker arrow. Okay, so $75 to take the AP exam. And of course a lot of work. When you get to college, you're talking usually $500 to $1,000 a unit. And chemistry in college is going to be a 4-unit class. I'm talking semester units now. So, gosh, if you can get a $4,000 class for $75, that's a really good deal. Your parents would love that. So, what happens if you don't do well on the AP exam? Worst case, you've invested $75 and some time in high school, and you've learned a lot of chemistry. And so when you have to take chemistry, if you're going into certain things like medicine or pharmacy or other classes that, even engineering, a lot of times you need chemistry. So if you're taking any of those kind of classes or majors in college, this is a compelling reason to think about getting the AP class in high school. And then, hey, you don't pass this exam, you've got a big head start on this very expensive class, and you're more likely to get an A and boost your grade point average. So that's it for now. I hope this has been helpful for all of you.